Hey statisticians, today we're going to look at a video where we're going to learn about and do some examples for learning about doing sampling distributions for the difference between two statistics. Now, if you remember back in the day when we first started talking about random variables, that actually, believe it or not, if we think about it, the statistics we calculate, like a sample mean or a sample proportion, things like this, these guys are random variables. Random variables. In other words, they're a variable whose values occur through some type of chance process, assuming that we're selecting our samples at random and independently and all that kind of stuff, right? And so the things that we learn about random variables are going to be true for sample statistics, right? For instance, when we were talking about comparing two random variables, we learned some formulas for the combinations of random variables. Remember, if you said that you had some random variable x that was independent from some random variable y, if you were trying to figure out, say, the expected value of x minus y, then very intuitively that was the same as the expected value of x minus the expected value of y, and that was so nice. And then we learned something that was kind of interesting, that you can't, that if you wanted to find, say, the standard deviation of x minus y, you actually had to first add the variances, right? And so that would end up being the square root of the variance of the difference between x minus y, and that ended up being, say, the variance of x, interestingly, plus the variance of y. And I'm not going to prove that to you here in this video. That was something that we learned back in the day, but this is absolutely true in the case. And so what we're going to see is this kind of mathematics that we learned way back in the day about combining two random variables together, we are going to use exactly here when we start thinking about a statistic as a random variable, right? And so, okay, that's great. What does that mean? Well, we're going to learn to do, we're going to look at the sampling distribution for two things really quick today. We're going to look at the sampling distribution for the difference between two proportions, right? And we're going to see that under special circumstances, that if you were to, say, randomly select some sample from some distribution where the population proportion was, say, P1, and then you were randomly select another sample from some other population who has a population proportion of P2, and you were just, say, take two random samples and subtract them, right? Then that distribution was going to end up being approximately normal based on a large counts condition, again, that we'll look at another time, based on a large counts condition. And we know that this normal distribution will be centered at the difference between these two population proportions, right? And so whatever this guy is minus whatever this guy is will be the mean of that distribution. And then we also learned, based on, we can prove this, but based on what we learned about the difference between two random variables, that the standard deviation of that distribution is really going to be the square root of the sum of the variances, right? And so if we think about what we know about a population proportion, we know that a population proportion standard deviation will be the square root of p times 1 minus p over n. Well, if I was to square that, then you would just have that guy that's in the inside there, right? Because we get rid of the square root. And if we were going to add two of those guys up, we have that right there, and take the square root of the whole thing. So this should be kind of intuitive, right? We're going to see something similar, basically the same kind of thing, when we look at the sampling distribution between the difference between two means. And again, this is two sample means. So say we took a sample mean 1 that comes from a population that has an average of mu1 and a standard deviation of sigma 1, and we took another sample from another population where we had mu2, great band, and sigma 2, and then we compared those two sample means, we subtracted them. Well, that will also end up being approximately normal, so long as the something like the central limit theorem holds. And it's not just something like, it is the central limit theorem, because the central limit theorem will get the normality of each of these two separate distributions. And then the mean of this distribution will simply be the difference between what these two population means are. And then, of course, we'll end up using that same formula where we know that the standard deviation for the sampling distribution of a sample mean is sigma over root n, right? And so if we squared that, you'd end up getting sigma 1 squared over n1. That's the variance over n1. Plus, if we did it again over here for the other distribution, we got that guy. So all these formulas should be kind of intuitive if you really learned what we learned back here. And it's deep in your brain. So let's just look at a couple of quick examples where we're actually put these formulas to the test, or rather just use them for something mildly interesting. Here we've got Joe and Frank. Joe and Frank are very competitive, and they both play basketball, and they happen to take AP statistics. So as it turns out, based on past performance, Joe is the better three-point shooter, right? Joe makes 60% of the free throws, while Frank only makes 50%, right? And so really quick, let's call this, like, I'm going to say PJ is 60%, right? And say PF is 50%. So we'll take note of that. And then on the flip side, we see Frank here. He scores more points per game, right? And Frank scores on average 16 points per game. So let me get a different color for that guy. Let's see here. Here's green. 16 points per game with a standard deviation of 4, while Joe scores 10 points per game with a standard deviation of 3 points, right? So I don't have a ton of space here, but I'm going to say mu, and this was Frank now, mu F was 16, sigma F was 4, and let's say mu J is 10, and sigma J is 3. Okay, so that's fun. And so they decide they're going to compare their performances after the next 30 games. And so that sounds like a fun thing. All right, so then you want to know what's the probability that Joe will have a better free throw percentage than Frank, and also what's the probability that Joe's average points per game will exceed Frank's, right? So, all right, this is interesting. Really the way to calculate these guys, and to think about it, is going to be in terms of these sampling distributions, right? So if we imagine first, we play 30 games. Now, we're going to have to make some deep assumptions here, which are probably not entirely true in these scenarios, but we're going to have to make this assumption that these 30 games, right, are some kind of random sample of games, right? And more importantly, more than them sort of being just a random sample, we'll have to assume that somehow the performance on every single one of these 30 games is completely independent of the others. I don't know if that's really the case, but the only way for this math to work, guys, if we using the methods that we know here in AP Stat, is that if we assume the performance in all of these games is going to be completely independent of the others. So, all right, let's first think about this first problem here. What is the probability that Joe will have a better free throw percentage than Frank, right? Well, if Joe has a better free throw percentage, then we're trying to look at the probability, say that the probability of P hat J is greater than the probability of P hat F. In other words, P hats represent just how they happen to do in this random sample of 30 games. Even if Joe scores a higher percentage than Frank in general, it doesn't mean that he necessarily will in these 30 games. So what's the probability that his percentage in these 30 games is greater than the probability of Frank's? Now, of course, this is going to just be based on the probability that P hat J minus the probability of P hat F is greater than 0. And you can think for a second about why that makes sense. It's because all we did was subtract P hat F from both sides, right? So these guys, again, are two random variables. So let's look at this problem first. I'm going to kind of go... let me grab another sheet of paper, and I'll do this problem here on another sheet of paper, kind of like this, okay? So what do we know? Well, we would have to check the large counts condition here to verify that both of these two separate distributions should be approximately normal. And so in other words, we'd have to think, what's 60%? Think about the worst case scenario. 40% times 30 is 12. I'm really doing this informally, but you need to expect at least 10 successes and 10 failures for each of these two players across these 30 games. And you can do the math, but you could do 60% and 40% of 30, and then 50% of 30, and verify that both of those are at least 10, and go ahead. And that will get the normality of the distribution. So we should know that the distribution of P hat 1 minus P hat 2, actually, let me call this, what was this? P hat J minus P hat F, right? Let's say that this distribution will be approximately normal by the large counts condition, and its center will be the difference between these two guys. So I'm going to do this, I don't even need a calculator for this, but 0.6 minus 0.5, that's 0.1. And so I know that on average, the difference between their free throw percentages, 3-point percentages are going to be, wait, why did I talk about free throws here and 3-pointers here? That's stupid. What was I thinking? All right, I'm not going to start this video over. I'm just going to cross this out, free throw, and write 3-point. I just realized I'm talking about different things. It doesn't even make sense. Did you guys notice that? Oh, well, you might have, you might not have. But let's just say I know about 3-pointers. Let's change it to 3-pointers. So anyways, sorry, I apologize. We got 0.1 there as our mean. And then for the standard deviation, we're going to have, okay, I'm going to even write this guy out. We'll have a big square root, right? And I'll write out the work here. You end up doing 0.6 times 0.4 over 30 plus 0.5 times 0.5 over 30. And it actually, as you can see, it actually doesn't matter that they both have the same sample size in this formula. It just is coincidental here that they did. But so that's no big deal. Let me just calculate that in my calculator here. So we got 0.6 times 0.4 divided by 30 plus, supposed to be plus 0.5 times 0.5 divided by 30. We got that guy. That would be the variance. And I take the square. Clear. the set square root of that guy, and there we have our standard deviation, which is not insignificant, right? I'm going to store that in for x so I can get to it quickly easier, but that's the standard deviation of results. So this guy was about 0.1278. 1278. And again, I'm just going to write this underneath here so I don't know, the same color makes me feel better. So all right, so we have this. Now, if I want to know the probability that some p hat j minus some p hat f is greater than 0, I can just do normal CDF with this information here, right? That's just, I've got this normal distribution like this, and I've got 0.1 in the center, and I've got a standard deviation of 12.78. Does that make sense to me? Oh yeah, yes it does. Because I can get, obviously, negative values. Doesn't it make sense that we could have negative values here? Of course, I'm looking for all the positives that end up being positive. So actually, if you think about it, one standard deviation below the mean here, right, is going to end up being some kind of negative value, right? This will be around, right here, negative 0.0278. Now my handwriting is getting so small, you can't even read that. I'll have to write bigger, I apologize. The idea is that I'm going to calculate for this normal curve the area all the way this way to the right above wherever you're going to get 0, right? Because I want the probability of getting something greater than 0. So if I go in my calculator, I'll hit second vars, I'll go to normal CDF. My lower bound is going to be 0. My upper bound is going to be positive infinity. My mean is going to be 0.1. My standard deviation is going to be, I'm just going to, actually, I can type x because I stored it in for x. That's a cool little fun trick. And then I'll calculate, and I got 78.3%, right? So what's the probability of this happening? About 0.7830 as a probability. And that should make sense that Joe actually has a higher probability of this occurring because, of course, Joe had a higher percentage, right? Joe is supposed to make make more free throws than Frank. And so the fact that it's 78%, it's higher than 50%, should make sense because he seemed to be the better shooter. All right, so that's one way that we could use the sampling distribution for, say, p hats. Based on that sort of formula there. Let's try to answer the second question. What's the probability that Joe's average points per game exceeds Frank's? I'm going to just do it on the piece of paper here itself. We've got enough room. So, okay, similar to what I did here, we need to look at the sampling distribution, right? So again, we're treating that each of these performances as independent of each other over the next 30 games entirely, again, which is maybe not the best assumption, but it's the only way this math is going to work, and so, hey, let's do it anyways, right? Again, so this time I want to know the probability that in case that p hat j is greater than p hats. Am I talking about p hats here? No, I'm talking about averages. So it's going to be the probability that x bar j is greater than x bar f, right? And of course, we're going to use the same basic math to convert that to a difference. That means x bar j minus x bar f is greater than 0, right? And so the only way that I can calculate this is if I know something about the distributions of the differences between these two sample means, right? So I could say this x bar j minus x bar f, right? What's the distribution of this guy? Well, it will end up being approximately normal. Why? Because since I'm doing 30 games, this distribution will be approximately normal, and this distribution will be approximately normal. Why? By the central limit theorem. Isn't that beautiful, right? Now, the center of this distribution is going to be the difference between their two results. Now, here we got to pay attention to order, right? That, in fact, this guy, remember, Joe's average was 10 points per game. Frank's was 16 points per game. But notice that this is actually going to be a negative average because 10 is less than 16. So this is going to be 10 minus 16, 10 minus 16, which is what? Negative 4. I'm going to write that in black. Negative 4. What am I saying? Negative 6, right? And then the standard deviation of this guy now is going to be a big square root formula again. So we'll do a big square root. But this time, I'm going to take the standard deviation of this guy, and I'm going to square it. So that'll be like 3 squared over 30 plus this guy, 4 squared over 30, kind of like that. And then we'll calculate this guy out and see what the standard deviation ends up being. Let me get my calculator. Why is that the case? Well, just like we saw, you're summing the two separate variances. Remember this formula? When you square it, when you square it, you get sigma squared over n, and that's essentially what goes on inside each of these guys here, and that's where we got this formula from. So, okay, let's just calculate that really quick. 3 squared plus 4 squared actually is 25. 25, that's fun. So I'll have 25, I can do some of this math in my head. We'll have 25 divided by 30 is that guy, and I'll take the square. Why did I did the same thing again last time. Square root of that guy, and I have this, and I'll store this in for x now just to save some time. And so that will be my approximate standard deviation. It's about, let me get my black marker, 0.9129 about, right? And so, okay, now if I want to calculate this probability that the difference, probability of x bar j minus x bar f is greater than 0, right? Now, once again, I'm going to have a little normal distribution. I'll draw it over here this time. You don't even actually have to draw the normal distribution. This time, the mean over here is negative. It's -6. And so 0 is going to be somewhere over here on this side. And I'm guessing this probability is going to be, oh my gosh, if that's the standard deviation, and that's this standard deviation, this value is going to be pretty much 0. Because if I go up 3 standard deviations, that's just going to be over here at about, what, -5, -4, -3. So there's basically no chance this is going to happen. But so be it. Let's see what happens here. Let me go to normal CDF. I'll make my lower bound 0, right? And 0 is going to be like, where the heck is 0 on here? I'd have to calculate it z-squared even. It's somewhere like way. It's like even me putting that there is doesn't even make sense. But I'll say 0 to positive infinity with a mean of -6 and a standard deviation. Once again, since I cheated and I stuck the x in there, we can go like that, and shazam, holy moly. Look at that. Basically no chance whatsoever. The probability is 0. 0 ... So many zeros. 2484, right? And how many zeros were in there? Oh, there'd be like 10 zeros here. What the what? Right, that says 10. That's really tiny. And so no, I mean, this is so low. I could write it in scientific notation like it has there. 2.484 times 10 to the -11th, which basically means it's approximately 0. There's almost no chance that Joe is going to score more points on average over a course of 30 games than Frank. It's just there's too much of a disparity. However, there is some chance that maybe Frank could do better than Joe. Remember our other paper? Where'd that other paper go? That's over here, right? Remember, the probability that Joe has a better three-pointer percentage than Frank was 78.3%. So the probability of the flip side would be 1 minus that. So there is some chance that Frank might overtake Joe in three-pointers, but there's basically no chance that in terms of their average points per game that Joe will. Of course, you never know. This is all assuming that their performances are fixed, right? That these parameters are never going to change. And of course, it's possible that if we think about how these probabilities might not tell us the truth at all, we could realize, well, number one, people actually improve in these sports. And so if people's performances are going to actually changing and not based on a fixed mean and standard deviation, then we're going to see maybe this is a higher probability than we really think. Maybe Frank is going to get better, right? Also, we're also assuming here that every game is completely independent of the other. And we know that that's probably not the case, that, there's fatigue, there's also developing of skill. And so there's reasons why people might do better or worse on average than they had in the past, right? And of course, and if they're both playing games at the same time against each other, how could their performances be completely independent if they are in direct competition with one another? I don't know. So there's lots of fundamental assumptions behind this math that might not totally hold in this scenario, but nevertheless, it does tell us something interesting. Guys, I hope this is helpful for you. Remember that ultimately what we were looking at here were two different sampling distributions. The sampling distribution for the difference between two proportions. And in this case, we were looking at two sample proportions drawn separately from two separate populations with fixed parameters for P. And here we looked at the sampling distribution for the difference between two means, where we were drawing those two means randomly from two different populations, one with a mean of mu1 and a standard deviation of mu1. And here a second mean from a distribution with mu2 and a standard deviation of mu2. Remember, we're taking some sample mean from this guy and some sample mean from this guy and looking at their difference. So, folks, I hope this was helpful to you. Have a beautiful day and enjoy working on some problems. I'll catch you on the flip side.